Section 4.1 is going to talk about probabilities. So what I had you doing before I started the video was simulating some coin flips. And of the 28 coins, trying to get, even 20 of them to be heads or 20 of them to be tails or more, that's pretty tough. But winning the Mega Millions jackpot is like getting all 28 of these to turn up heads. Man, the odds of that are pretty small. But the odds on that are reflective of probabilities, which is where we're going in section 4.1. So let's talk about some things about probabilities. So first of all, probabilities are going to be a number denoted between 0 and 1. And those numbers in there represent various degrees of certainty. So if something happens with probability 1, then it's guaranteed to happen. So I'm not sure if it was Benjamin Franklin or not. It seems to be who's coming to mind. But he said that there's two things that happen with probability 1. Does anyone know what those are? Probability 1, death, and taxes. All right, so those are certainties. Now, on the other end of the scale, virtually impossible, maybe just above the 0, is probability of winning the Mega Millions. Which, for perspective, is like the probability of flipping a coin 28 times and getting heads 28 times. So, very, very unlikely. So, and then there's things in between there. Now, all your probabilities are between 0 and 1. If you want to make it easy for me to grade one of your problems on an exam, give me an answer outside of that range 0 to 1. It'll be very easy for me to grade, and I appreciate the easiness of grading that. Now, in determining probabilities, there's 3 different approaches that you can use to determine a probability, or at least estimate a probability. One of them is the relative frequency approach. You can look at how many times a procedure is run and how many times an event occurred. So that's kind of a relative frequency approach. You could use that to determine the likelihood of a car crash. You can find out, well, how many automobile accidents are there in a given time period divided by how many cars are out there on the road. And that would give you a relative frequency approach. Another approach to finding probabilities is the classical approach. This requires that you can list all the possible outcomes of an experiment, and then you want to figure out, well, how many ways can it occur? So we'll look at that when we talk about, say, flipping a coin or the number of boys amongst, 3 babies born at a hospital, that kind of thing. And finally, there's subjective probabilities. That's when somebody just gives you their best guess based on specialized knowledge that they may have or understanding of the circumstances surrounding something. It's just kind of an educated guess. Now, we're not going to do a whole lot with example 3. There is one kind of tongue-in-cheek example about that coming up. But those are the 3 different ways we're going to have to look at probabilities. And keep in mind that probabilities are always going to be between 0 and 1. So a couple more examples, concrete examples of these different approaches. In terms of the classical approach, when trying to determine the probability of winning the grand prize in a lottery by selecting 6 different numbers between 1 and 60, each combination has an equal chance of occurring. That's important. That's definitely important for your classical approach, that each combination has an equal chance of occurring. So the probability of winning is 0.00000002. All right. Like I said, about the same as whether you play or not, but that's your probability. We'll be able to calculate that kind of stuff in Chapter 4 after we do Section 4.4. Finally, subjective probability when trying to estimate the probability of getting stuck in the next elevator that you ride in. we know that from personal experience, the probability is quite small. Let's say it to be 0.001, about 1 chance in 1,000. Probably even less than that. I've never gotten stuck in an elevator, nor have I known anyone to get stuck in an elevator. But all these are different probabilities, and we want to take a look at the numbers themselves and what should be perhaps an easy question for an exam. So we're going to look at problem number B and try to determine, well, which one of these are actual probabilities. So I'm going to look at that here. Identifying probability values. Which of the following are probabilities? What was the range I gave for probabilities? They had to be between what numbers?
0.
0 and 1. So which one of these can I get rid of? Actually, I can keep 0, right? What does it mean for something to have probability 0?
That's never
No
happened.
chance.
Never happened.
Oh, then-
Now, I've kind of changed my mind after their last season, but I used to joke that probability of the Lions winning the Super Bowl was 0, all right? Maybe it's a little bit bigger than 0 now. They did seem to do okay last season. Yes, sir.
You'd be able to get rid of 2, right? Because it's not between 0 and 1.
Yes. So we can get rid of that one. Good. What else can we get rid of? Ivy?
The negative.
Yeah, the negative one for sure. Can't have negative probabilities at all. Let's keep going. These are good so far. Someone from my Zoom? Oh. I'm not sharing my screen. Bad on me. All right, so there we go. Thank you. Let's keep going. What else can I get rid of? What else is certainly not a probability? Gerald?
250%.
Yeah, 250%. That's not a probability. There's 2 more that strike out or, stand out to me, and it is 7 to 3 and 5 to 1. Those aren't probabilities at all. Those are odds. And we will learn to work with odds at the end of this section. But right now, it's just not a probability. What else can I get rid of?
5/3.
Yeah, 5/3. That's bigger than 1. Thank you. And then finally, I'm not a big fan of 50 minus 50. I think what they're trying to imply is that there's a 50% chance, a 50-50 chance, but I'm not really a big fan of that one. I would just leave this one off from an exam. I guess, the other way you could see that is, well, 50 minus 50 is 0, and 0 is a legitimate probability. So, okay, I get that. I don't know. I'm not a big fan of that one. I wouldn't put that on an exam. Now, a lot of times in this class, we're going to do things with either the relative frequency approach or the classical approach. The classical approach requires that all of your possibilities are equally likely. Now, if you were guessing as to who discovered penicillin first, was it Marcel Beach, William Penn, Johannes Salk, Alexander Fleming, or Louis Pasteur, what's your chance of guessing correctly? Well, let's see, we've got 1, 2, 3, 4, 5. What's your chance of a correct guess? Yeah, it's 1 in 5. And if you're like me and did not know the correct answer was Alexander Fleming, then you can feel better. I didn't know that one. For a second I thought, didn't he write the James Bond novels? But no, that was Ian Fleming. So if you got confused like that, you're in good company. A lot of times when we write things, we use P of something to denote the probability of this event. Often I'll use a letter here to represent, the event of guessing correctly. So I might just put P of C, where C represents the event that I guessed correctly. Let's take a look at example D. In a Pew Research Center survey, randomly selected adults were asked if they have seen or have been in the presence of a ghost. 366 of the respondents answered yes. 1,637 of the respondents answered no. Based on these results, find the probability that a randomly selected adult says that they have seen or been in the presence of a ghost. So let's just do this here for ease. Let's see, where is it? Seen or been in the presence of a ghost. This much right here. I'm going to let that be event G. So G is seen or been in the presence of a ghost. So what this problem is asking you to calculate then is, well, what's probability of G? What's the probability of that event? Okay. Now, if you look carefully at the problem, I added a little bit of a note here. I said, don't just divide the first two numbers that you see. A lot of people, when they look at this, are tempted to say, oh, well, 366 divided by 1637. That would be wrong. We got to think a little bit deeper here. Now, the 366 part, that's our numerator. That's how many ways that this event could come out. But what's the total number of possibilities? How would I find that?
Add those two.
Yes, thank you. Yes, thank you both. So it's going to be 1637 plus 366. That's how many people were surveyed. There's a total of 2,003. And 366 of them have seen or been in the presence of a ghost. So now for the most part, I'm happiest if you leave things as a fraction. Occasionally, maybe I'll want a decimal. Maybe some of the answers are just going to be decimals, and that's fine too. But for right now, let's just leave it like this. I'm not even really worried about lowest terms, although sometimes I do appreciate it if you write it in lowest terms. I'm not going to worry about it. Let's move on to the second part of example D. I'm going to let you look at that before I finish or before I quiz you on it. In a particular survey of internet users, 3,782 respondents say that they use social networking sites, and 1,373 respondents say that they do not use social networking sites. What's the probability that a randomly selected person uses a social networking site? Does the results suggest that it is likely? That means a probability of 0.5 or greater for someone to use a social network site. All right. So S is at the event a person uses social networks. And I want the probability of S. What's the probability of that event? You can just tell me how it's calculated. You don't necessarily have to give it to me down to the nearest thousandth of a decimal place. That's a good question. I don't know off the top of my head, but that sounds reasonable. What numbers did you divide to get that? All right, so what you're doing then to figure out how many people were surveyed is you're adding up these two numbers. 1,373 plus 3,782. So 3,782 over what? 51? 55. Yeah, and somewhere a little north of 70% seems reasonable. Like I said, more often than not, I'm going to be happiest with a fraction, because sometimes when you convert things to decimals, it sort of hides aspects of the problem that could make it wrong or make it right. So where I really care about it, I will say leave your answer as a fraction. Lowest terms doesn't bother me. And if you want to put it in lowest terms or not, this is not a math class. I'm not worried about that aspect of it. Yes?
This is using the classical approach, right?
Yeah, this is using the classical approach. So we're assuming that each one of these is equally likely. So, and that's reasonable here. There is one little nuance that I will mention here, and that is we're talking about randomly selecting a person that uses social networks. Well, really, this probability only pertains exactly to the people that were in the survey. We're kind of assuming that this probability could be generalized, which I'm okay with because it was a survey of internet users. It wasn't like a website where people went to and expressed their opinions. It's not a voluntary response kind of thing. You're chosen to be in this as opposed to not. So I'm not worried about the voluntary response aspect of this. This is probably representative of, you know, the broader adult population. Are we okay with the second part of example D here? Let's move on to example E, and I need to introduce you to something, some vocabulary. It's called your sample space. This is a collection of the results of an outcome or of a procedure or experiment. So sample space is a collection of the outcomes of an experiment or procedure. So it's everything that can happen when you do your experiment. And for example E, they want us to look at the sample space from 3 births. So you go to the hospital, you watch the next 3 babies that are born, and you find out their gender. So let's see what the sample space is going to look like. Now I'm going to enumerate it this way. So our sample space you could have a baby girl, and then another baby girl, and then another baby girl. So you have 3 girls. Or you could start out with 2 girls and then have a boy. Or you could start out with a girl, and then a boy, and then another girl. And finally, a girl, a boy, and another boy. Now, because there's 3 babies being born and there's 2 outcomes per each, you expect a total of 8 items in your sample space. So the next thing I can look at is there's a boy followed by 2 girls, a boy, girl, and a boy, 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 and girl. And what's the last one? All boys. So this whole collection of outcomes, that's your sample space. Those are all the possible things that could happen when you're looking at the possibility, or when you're looking at the event of, not the event, but the experiment of 3 babies being born, looking at their gender. Now, you could combine these in certain ways. You could say, well, you know, there's a couple ways you could have 2 girls, actually 3 ways, 1, 2, and 3. There's 3 ways you can have just 2 girls, etc. But before I get to that part of it, are you okay with our sample space? At least it matched our calculations. We expected 8, we got 8. So I don't think there's any combination that I left out. The next part of this says, find the probability of exactly 2 girls. Well, I'll tell you what, we're going to do a little bit better than that. So number of girls and the probability of that number. Probability of X. So there could be 0 girls, 1, 2, or 3. Let's start out with the probability of no girls. How many of these points in the sample space represent the possibility of no girls? 1. And there was 8 possibilities that are there, so the probability of having 3 girls is 1 out of 8. How about the probability of 2 girls? So let's take a look at the probability of 2 girls, or actually 1 girl, I should say. We'll do things in order. Probability of 1 girl. Well, that could happen here. Where else? Here. I'm only seeing 3. Because if you're looking for exactly 1 girl, then it'd be any of the yellow dots here. Just the order. Just the order. Now, there's certainly, you could say, well, wait a minute. This is just, this is just having one girl, and that can happen in 3 ways, but the net effect is just having 1 girl. And I agree with you. But this event can happen in any of those 3 ways, so that's why there's a 3 in 8 chance that you'll get 1 girl amongst 3 babies. There's likewise a chance that you get 2 girls. And try and identify the events that represent exactly 2 girls. One, 2, and then 3. So I think I got that right. I'm only seeing 3 here. Did I miss one?
No.
So 3 out of 8 is your probability there. Finally, there's a probability of 3 girls. What's the probability of 3 girls? How many ways can that occur? Just 1. 1. There was a story on the news about a family who was trying for their 14th kid because they had 13 boys. It's like, wow. 13 boys. Yeah, I have no idea how they can afford that. But 13 boys, let me do a quick mental calculation here. The odds of that are 1 in 8,192. Wow, that's certainly beating the odds there. All right. Problem E asks you 2 questions. It asks you for the probability of exactly 2 girls. And we've already got that probability, right? That probability was 3 out of 8. But what if I change that to probability of at least 2 girls? How would that change the calculation?
4 out of 8.
4 out of 8, good. Because you'd have all 3 of the orange dots plus the blue dot. And that gives you a total of 4 dots out of 8. Now, as I said earlier, I don't really care if you put this in lowest terms or not too much. I mean, I'm happy when you do, but it's okay. 4 out of 8, 1/2. Either answer is going to get full credit. So once again, to kind of reiterate. Sure. Well, if you look at the number of events that satisfy this, all the events that have at least 2 girls, those are going to be the ones with the orange dots or the blue dot. So there's 1, 2, 3, 4 different events that satisfy that, that's my numerator, divided by the 8 total, that's my denominator. So there's 4 ways out of 8 that can happen. You're welcome. Thanks for the question. Let's keep going with example F.
Can I see that one more time?
Yeah, sure.
Thank you.
You're welcome. Now this is going to take me a minute, but I'm going to write out the sample space for example F. Because we're going to talk about something else called the complement. So this is going to be the sample space for 4 babies. If you want to copy this down, great. If you don't want to copy it down, I don't blame you. And my apologies, I'm going to have to think for a moment. So give me a second here. So it'll be M, 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 M. So 4 males. And then M, 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 F. For 3 males and 1 female. M, M, F, M. And M, M, F, F. So there's 4. Now overall I expect 2 times 2 times 2 times 2. 2 possibilities for the first kid, 2 for the second, 2 for the third, 2 for the fourth. I expect 16 points in my sample space. So I got a lot more work to do. There's M, F, M, 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 F, M, F, M, F, F, M, M, F, F, F. So I'm halfway there. Now I got to start changing up this first letter. That's going to be F, M, 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 F, M, M, F, F, M, F, M, and F, M, F, F. And finally, the last 4 here, F, 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 M, M, F, F, M, F, 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 M, and finally the last one, F, F, F. So that's my sample space for those 4 kids. My condolences to you if you chose to try and copy this down. There's your sample space. Let's take a look here at the question then. And where did I put my handout? Event A is the event 4 randomly selected births result in girls. And they tell us the probability is 1 in 16. Do you agree with that? Probability is 1 in 16. Now we can assume that these are equally likely events because we're assuming that boys and girls are born at a rate of 50%. That's not exactly true, especially in certain countries. But for now, let's just go with that 50-50 rule. This is event A. That's event A. Event A. We're going to have to work with something called the complement. And the complement is going to kind of mean the opposite in some way. It's not exactly the opposite. Opposite's not the right word. Complement's a better word. So if my event is rolling a 6 with a single die, the event of not 6 would mean rolling a 1, 2, 3, 4, or 5. It's just like everything else. So let me write down a few examples of a complement. The complement of an event denoted by the bar notation consists of all outcomes in which the event does not occur. So I'll give it to you graphically, and I'll give it to you with some examples. Examples using the complement. So event S is the event of rolling 6 with a die. S bar is the event of rolling anything but a 6. So rolling 1, 2, 3, 4, or 5. So there's the event or not the event. Let's do another one. W is the event of winning. What do you think W bar is? What would be the opposite of winning?
Not winning.
Not winning, yeah. Event of not winning. Maybe that means you tied, maybe that means you lose. It just means you didn't win. And let me give it to you graphically. Yeah, I'm going to do it graphically though. So let's say this is our sample space. This is everything that can happen. Let's put event C here. That's the event of C. So C is everything on this side of the sample space. Then everything on the other side of the sample space is C bar. So you're either here or you're here. You're in one of these or the other. Your heads or tails, you're male or female. You're one of those. So you're the event or its opposite. So, or its complement is probably a better thing that I should coach myself into saying a little more frequently. Your event or your complement. So one or the other. Now between the two, that's like everything that can happen. Let's look back up here. There was somebody who was still curious about this event or this event. So you win or you don't win. Those would be those two complementary events. Up here, event A is that you get all females. So event A, all females. What would A bar be? Is the event of what?
Anything other than all
Males.
females?
Yeah, anything other than all females. All right, so this is A. Let me put in green here. Everything else. So what's in green is A bar. So this is the event of, well, you have to have at least one male to be in A bar. The event of at least one male. At least one male. That's the complement of A, is this A bar. So you're one or the other. And between the two, A and A bar, that covers everything. There's nothing left out. You're either an A or A bar. Okay. Now, we can use that idea of A and A bar in the following way. Before I move on, Are you okay with the idea of an event and its complement? Doing all right there? All right, I can see people that are here. There's a lot of people at home, a lot of people without their cameras on. I can't really see, so I can't judge too well how you're understanding. Look here. Example E. Yeah. Well, it depends what you define as, I could use event A as being exactly 2 girls. So if event A is the event of exactly 2 girls, let's think about what A bar would be. That's a great question. What would A bar be? Well, it's the event of something other than exactly 2 girls, right? So it'd be the event of 0 girls. What else could happen?
1 girl or 3 girls.
1 girl or 3 girls. Yeah. So that would be an example of A and A bar. So, you know, what A and A bar is going to depend on where you start. I mean, when you start with your event A, then you can figure out what A bar is. But does that help out a little bit for you? All right, thank you. Now, the cool thing about the complement is that you can actually use that to help you do some calculations. So for instance, here's the rule of complementary events. The probability of A plus the probability of A bar has to be 1. Now what's that saying? Well, like for this example, the probability of all females plus the probability of at least 1 male, well, that's everything. The probability that you're going to get one of these has to be 100%, because that's everything that can happen here. So the probability of A plus the probability of A bar is 1. That's fine as far as it goes, but this is where it's really useful. The probability of A bar is 1 minus the probability of A. Basically, all you've done is you take this and move it to the other side of the equation, and you get this here. Now that can be helpful in problems like example F, where you calculate things not directly, but indirectly. So we're going to start using some rules to calculate our probabilities rather than just relying on enumerating the sample space and saying the number possible by the total number of outcomes, or the number of ways an event can occur over the total possible outcomes. Let's look at this one. A certain group of women have a 0.43 rate of red-green color blindness. If a woman is randomly selected from this group, what's the probability that she does not have red-green color blindness? Now I'm going to start out by letting RG be the event. A woman has red-green color blindness. I'm just going to abbreviate it here because I'm running out of room. So RG is that event. And I can make this observation. They tell me what the probability of RG is. What's that probability? Probability of red-green. Well, it's this right here. 0.43%. Now, if I turn that into a decimal, it's 0.0043. You're going to move that decimal point 2 places to the left when you convert that to a decimal. But RG is not what I want. The probability of RG is not what I want. I've already got that. What I want in this problem is the probability of RG bar. probability that somebody doesn't have red-green color blindness. How do you suppose I'm going to get that? They didn't tell me about what that was.
1 minus probability.
Subtract from 1. Thank you, ladies. So it's going to be 1 minus the probability of RG, which is 1 minus 0.0043, which is 0.9957. Beautiful. So you're getting something indirectly by using the complementation rule. Okay. Well, the total of these probabilities should always equal 1. Probability of A and probability of not A, that should always be 1. And then if that's true, then you can get the probability of A bar or the probability of A, you can get that indirectly. And that's going to be a real helpful thing when we work more into chapter 4 and chapter 5, using this complement rule. It's going to be a lot easier sometimes to calculate things with the complement rule than it would be to calculate things directly. So, yeah, thanks for the question. Let's take a moment and look at something called the rare event rule. This is for probabilities. So let me switch over to here. And let me see if I can't make that a little bit bigger here for us. Now suppose I took out a quarter and I flipped it 30 times and got heads each of those 30 times. Actually, let me do it 20 times because I actually know the numbers for 20. If I flipped it 20 times, the chance of getting ahead 20 times are 1 in 1,048,576. Now, if I did succeed in flipping it 20 times and getting all those heads, would you think that I was lucky, or would you start to think that the coin was maybe biased? That it really wasn't a 50-50 chance that I was actually getting 20 heads in a row? Which one of those would you think?
The coin.
Yeah, probably start thinking there's something going wrong with that coin, right? Because it's really unlikely. Now, one of two things is happening to you when you make that decision. Either you got it right or you got it wrong. So, given the circumstances, you've got two things you can believe. That either I got really lucky, or that your assumptions that you have an unbiased coin, meaning you got a 50-50 chance of heads or tails, is wrong. And that's what the rare event rule is saying. Saying if under a given assumption, the probability of an observed event is very, very small, then, and the event occurs significantly less or significantly greater than what we would typically expect, with that assumption, we conclude our assumption's probably not correct. So if I'm getting more heads than you think I should by flipping that coin, then either I got really lucky or your assumption that it was a fair coin is probably wrong. Now the benchmark for significantly high or significantly low is going to be set at 5%. So if something happens with less than a 5% chance, then you're going to start questioning your assumptions. Like, well, it's not very likely that this would happen with these assumptions. So I think my assumptions are wrong. That's the essence of the rare event rule. So let's take a look at example G here. Y-sort gender selection. Microsort's Y-sort gender selection technique is designed to increase the likelihood that a baby will be a boy. You can also do this for girls. At one point before clinical trials of the Y-sort gender selection technique were discontinued, 291 births consisted of 239 baby boys and 52 baby girls. Based on these results, what's the probability of a boy born to a couple using Microsort's Y-sort method? Does it appear that the technique is effective in increasing the likelihood that a baby will be a boy? Well, if it was a 50-50 chance, then you'd probably expect maybe, I don't know, 145 around there, 145 boys. You're doing way better than that. So if we just take these as the basis for our probability, 239 divided by 291, that's a pretty big step up from the 50-50 that you would expect without this method. So 239 divided by 291, 82%. Wow, that's really high. So about 82%. Now, one of two things could happen. Either they got really lucky, astronomically really lucky, or what's the other conclusion that we could have about the Y-sort method?
It works.
It works. Yeah. That's a pretty inescapable conclusion here, is that it seems to work based on this data. So you're using the rare event rule in coming to that conclusion. You're rejecting the hypothesis that it's a 50-50 chance for a boy or a girl. Let's move on to example H. On their first date, Kelly asked Mike to guess the date of her birth, not the year. What's the probability that Mike will guess correctly, ignoring leap years? Someone from the chat, someone on Zoom. What's the probability that they're going to correctly guess her birth date? Yeah, 1 over 365. Would it be unlikely that on your first guess you'd get the birthday right? What do you think?
Would be unlikely.
Yeah, it'd be very unlikely to get it right on the first try. If somebody did guess your birthday correct on the first try, then would you believe his claim that he made a lucky guess, or would you be convinced that he already knew when you were born?
I already know.
New.
Yeah, I'd have to say already knew. All right, already knew. Already knew. And here's a subjective probability for the last one, and it's a little tongue-in-cheek. If Kelly asked Mike to guess her age, and Mike's guess is too high by 15 years, what's the probability of a second date?
2.
Let's go with 0 because it's probably pretty unlikely. Now this is the subjective part, but it's, you know, I would accept on something like this an answer of 0 or very close to 0. All right. I don't think it's a good idea to tell somebody that they'll look a lot older than they are. Sweet. How are we doing so far in the first few examples? All right. Let me stop things here and we'll pick it up in a couple minutes with a discussion about odds.